Okay, for what we have in looking for the inverse Laplace transforms of what we have for a given function, and we have in this problem we have the Laplace transform is equal to the reciprocal of the product of s squared times the quantity of s squared plus 1. And if we're looking at utilizing integration, now we have with our technique, now we must have a monomial factor in S in order to take this particular integration approach. So looking for the function f of t. So that is going to be the inverse Laplace transform of 1 over s squared times the quantity of s squared plus 1. And if we look at utilizing the integration pathway, okay, so we're going to have tau as the variable of integration. And okay, so we're looking at the inverse Laplace transform, and you have of s times f of s. So once you multiply this Laplace transform by s, you're going to have the degree in the monomial, which we have at s squared, that is just going to go to s. So like s times the reciprocal of s squared will go to 1 over s. So we're going to have what will be the inverse Laplace transform of not 1 over s squared times the quantity of s squared plus 1, but the reciprocal of s times the quantity of s squared plus 1. And once we take the inverse Laplace transform of this, okay, we're going to integrate, okay, and again, the variable of integration will be tau. And to be able to integrate, what we have here, we're going to be taking the partial fraction decomposition of s times f of s. Okay, so for what we have in the partial fraction decomposition of 1 over s times the quantity of s squared plus 1, now again, s is a linear factor, so we have a over s. Now we have with s squared plus 1, we have a quadratic factor, and we will have the numerator to be 1 degree less in s than the denominator. So the numerator terms will have it bs plus c. And looking at clearing out the fractions, okay, so 1 is equal to a times the quantity of s squared plus 1, followed by the addition of bs squared plus cs. And now there's only one 0 that we can use, and that is the number 0 itself. And so if I plug in 0 for s, okay, we're going to have the terms in b and c will go out, and we're going to have a on the right, and with 1 on the left, okay, we have 1 is equal to a, so we have established that a is equal to 1. Now, we can utilize various values of s that we can plug in, and with this type of setup, I chose additive inverses with negative and positive 1, so I could set up a system of equations and not even have to worry about doing something like taking a matrix and performing reduced row echelon form layouts. And so if I plug in negative 1 for s, okay, we have like a is already established at 1, and the square of negative 1 is 1 plus 1 is 2. Then I have plus b times the square of negative 1, which is positive b, and c times negative 1 is negative c. And subtracting 2, we have, for this equation, we have b minus c is equal to negative 1. And if I plug in positive 1 for s, okay, we're going to have what will be b plus c is equal to negative 1. And with the addition method, we're going to have negative and positive c to go out, and b in itself will add up to 2b. Negative 1 plus negative 1 is negative 2. And from this, we have b is equal to negative 1. And if I plug in negative 1 for b in either equation, we get that c is equal to 0. And so for what we will have for the partial fraction decomposition, okay, so we're going to have a over s is 1 over s, and b at negative 1. So this is going to be negative s all over s squared plus 1. And just putting back what we have here. Okay, so taking what we have with the partial fractions, okay, and integrating. Okay, so tau is going to be the variable of integration, And now we can itemize the terms and work with the individual Laplace transform items, but we can go ahead and do it in one sweep. For what we have for 1 over s, the inverse Laplace transform is going to be 1. And we have with negative s over s squared plus 1. So we're going to have a negative term. And we have the negative of s over s squared plus 1. And this will correspond to the cosine function. And with the variable of integration, so we're going to have that term is going to be negative cosine of tau. And integrating, we're going to have for d tau, antiderivative is going to be tau. And for the negative of cosine of tau, the antiderivative is going to be the sine of tau. And with the limits of integration going from 0 to t, so we have with the upper limit, okay, we have t minus the sine of t, and with 0, okay, now tau becomes negligible, and the sine of tau with tau at 0 is also going to be negligible. And so we have for the final result, we have t minus the sine of t. Okay, for the next Laplace transform, where we were looking at trying to find the function or the inverse Laplace transform on the basis of using integration. Again, so we had the Laplace transform is 1 over s squared times the quantity of s squared minus 1. And with this integration technique, so the s squared again is going to be lowered to first order. So we have with the integration pathway, so we're looking at the inverse Laplace transform of 1 over s times the quantity of s squared minus 1, and looking at what we have with the partial fraction decomposition. Okay, so for 1 over s times the quantity of s squared minus 1. Now s squared minus 1 is a difference of squares, so I can factor out s plus and s minus 1. So we have in the expansion, we have 3 linear factors. And for what we have in setting up what we have in the general case, all right, so we have a over s plus b over s plus 1, followed by c over s minus 1. And if I clear out the fractions, okay, so we're going to have 1 is equal to a times the quantity. So s goes out, and so a is going to be multiplied by s plus and s minus 1. And for b, okay, s plus 1 will cancel. So you have b times s times the quantity of s minus 1. And as for c, s minus 1 cancels. So we have c times s times the quantity of s plus 1. Okay, and so we have 3 variable expressions in s with s plus 1, s minus 1, and s itself. Until what? If we set s equal to 0, so we have 1 is equal to, and we'll have b is going to go out, c is going to go out, since both of these have s alongside them. Okay, but with a, with the variable expressions alongside it, s plus 1 and s minus 1, okay, we have 1 times negative 1, so we have 1 is equal to negative a, from which we're going to have that a is equal to negative 1. And if I apply the next 0, so if I set s plus 1 to 0, we'll have s is equal to negative 1. So we have 1 is equal to, and we have anything with s plus 1 goes out, so this will apply to a and c. Now for b, we got negative 1, and negative 1 minus 1 is negative 2. So we're going to have 2b. And from this, if 1 is equal to 2b, where we're going to have that b is equal to 1/2. And in the case of what we have for the remaining possible 0 to apply, we have with s equal to 1. So we got 1 is equal to, okay, now a goes out, and b is also going to go out since we have s minus 1 alongside both of these. And we have 1 times 1 plus 1 is 2, so we have 1 is equal to 2c. So we have 2c is equal to 1, and just like b, okay, we're going to have that c is equal to 1/2. So we have for the partial fraction decomposition, we're going to have negative 1 over s, and you're going to have plus 1/2 of the reciprocal of s plus 1, and you have followed by 1/2 of the reciprocal of s minus 1. And carrying over to what we have in the determination of the inverse Laplace transform. Okay, so we have here, okay, this set of partial fractions, and I have to take the inverse Laplace transform of each of them. Okay, so we have in the case of the negative of 1 over s. Now 1 over s, the inverse Laplace transform is going to be 1, but since I have the negative sign, we have negative 1. And for the reciprocal of s plus 1, this will be in reference to e to the negative t, or in this case, e to the negative tau. Okay, and with the coefficient 1/2 in front, so we're going to have plus 1/2 of e to the negative tau. And then we have for the reciprocal of s minus 1, you have e to the positive tau, and with the 1/2, that was already in reference to c whenever we had performed the partial fraction decomposition. Okay, so you got 1/2 of e to the tau, d tau, and taking the antiderivatives. Okay, so we got negative 1, antiderivative is negative tau. Then we have for 1/2 e to the negative tau, so that's going to be minus 1/2 of e to the negative tau. And then we have for 1/2 e to the tau, well, that is going to stay the same. And we have with the limits of integration, okay, so you have the lower limit is at 0, upper limit is at t, and just filling in. Okay, so from the upper limit, okay, so we have negative t minus 1/2 of e to the negative t, and we have plus 1/2 of e to the t. And now for the lower limit, okay, so you're going to have, okay, so tau goes to 0, and subtracting the lower limit, so you're going to have plus 1/2. Well, guess what? We have the last term, and subtracting, we have minus 1/2. So the constants are going to cancel each other. So for what we will have in the case of the final result, we're going to have negative t minus 1/2 of e to the negative t plus 1/2 of e to the t. And that will be the final result in the case of the attainment of the inverse Laplace transform.